So first off, who here has a copy of the welding handbook? Okay. Is everyone sitting next to someone with a copy of the welding handbook if you don't have one? Yes? No? If you are, if you're not, relocate so you're sitting next to someone who has a copy of the handbook, or you're near someone because we're going to be using it today. So it's okay if you don't have one, but make sure you're next to someone who does. So I've also got, I think, 2 more copies here if anyone wants to change their mind and buy one so I don't have to carry them back to the lab today. No takers? That's okay. Yeah? Yeah, absolutely.
No?
Yeah?
Gosh.
Yes?
Maybe next time.
Okay. There's still 2.
Unless you let people e-transfer you.
It's not going to me, I can't do e-transfer, it's going to the lab. So I'm not collecting the cash from you guys and just keeping it. I'm giving it to the lab manager for our group, so we can't e-transfer, unfortunately. No, I'm not supposed to let you guys do that either. I'm sorry. Because they're not mine. If it was my book, I'd let you borrow, but I need mine for class. But actually, I think we have probably a good amount of books here. It looks like we had at least one for every couple people, so if there is an issue and someone doesn't have one, let me know, but it should be okay. First off, everyone knows the exam is on Friday this week? Everyone's ready? 5 o'clock to 7 o'clock, ETLC E1018. Hopefully you guys all saw the topics were posted on eClass, basically covering up to everything that was up to and including last class. I think that's also in the syllabus. Does anyone have any questions? No? Awesome. So today we're going to be doing something a little bit different. This is actually what was going to be the seminar next week, but because we're 1 class ahead, it's going to be now the class today, which means we get a little bit more time for it, which is going to be good because I think this is going to be a fun class. So to start with, we're going to talk a little bit about this procedure handbook that I think I've been telling you about all semester. So for those of you who haven't, hopefully you guys have all seen this by now. This is an awesome book. So I personally actually have 2 copies. One was from a friend of mine who went through engineering about 15 years ago, and I got his copy and I have my own. If you're out in the world of welding and you knew nothing, even what was taught in this class, and someone came up to you and said, you know, I got to stick these 2 things together, how should I do it? The first place that I would tell them to go was this book. There's lots of other things out there, lots of other guides. I think we've included some throughout the semester. There's guides on MIG welding from Lincoln, there's guides from Miller. All the different welding companies provide kind of their own guides. This is also kind of from Lincoln. It's from the Lincoln Welding Foundation, but it's a little bit more separate, and I think the information here is not specific to any one supplier, any one manufacturer. All of this is generic. It applies to everything. And there's so much information here we can't really talk about it all, but I think we're going to talk about a little bit of it. So to start with, if you guys open this up, you're going to see in the index it's going to tell you all the stuff that's in here. We're going to be talking a little bit about carbon steel welding today, so hopefully those of you who have this can look and see that's going to be section 6. But first I want to just point out that there's so much in this book beyond what we talk about. Personally, my area of research is on distortion in welding. Residual stresses, thermal stresses, the results of those typically when you put them into a geometry that's the way you want it to be is you induce these stresses, and as a result, your geometry is going to change and deform to try to reach the lowest energy state. You don't want just high stresses in one region. It's going to develop reaction stresses everywhere else, and that's going to cause your geometry to change. And we're going to talk a little bit of that more later in the semester. But say you had an issue about distortion. What I can tell you is in this book, you're going to find equations that actually aren't that different from what we would come up with using the fundamentals we learned here. The only difference is most of the stuff in this book didn't come from fundamentals. This is kind of knowledge that was built from years and years of people welding and doing things and learning how to do things and how not to do things. So first off, I think this has been covered before, but we're just going to go over it again. In the world of welding, when you talk about a welding procedure, there's 2 acronyms that come up really frequently, and that's a PQR and a WPS. Does anyone know what these are? Sorry? Oh, the screen? Now I'm going to leave, if you guys can see it all right, I'm going to leave the screen up because we're going to use the whiteboard in a minute. Because most of today's class is not going to be me lecturing to you guys. We're going to be talking back and forth, and we're going to be getting some input from you guys. So, PQR stands for Procedure Qualification Record. So if you're out in the world and you're welding and you need to weld something, say you've got a pipe, and you want to weld a 1/2 inch wall thickness, 3-foot diameter pipe, you have to prove to the regulatory authority in Alberta, it's both the Alberta Energy Board, I think, and the National Energy Board, You have to prove to them that you have qualified this procedure and that you know exactly what's going to happen when you apply this welding procedure. And there's a code for pipeline welding, it's CSA Z662, that tells you everything you have to record when you prove that you know how to do this procedure. And that procedure ends up being written in what's called a welding procedure specification, or WPS. And this contains all the information that you would give to a welder to know how to make the weld. It's going to tell them what heat input range they're allowed, what voltage and amperage range they should be using to achieve that heat input, how fast they can be traveling, what electrodes they should be using, if there's a flux required, what flux they can be using, what position they can weld in, all of the information that you need to make a weld. All of that's in the welding procedure. But the way you come up with that information is by testing it and proving that when you use those parameters, you get the result you want. Whether it's a certain toughness, it's a certain strength, or generally a combination of the both. That's what goes in your welding or your procedure qualification record. That is the record of a specific weld made by a specific qualified welder, and exactly what they welded, what the parameters were, how long it took them to weld it, who was welding, and then all of the test results for that material. That is the test that proves that your procedure is good, but all of that information doesn't go in the procedure. The procedure is just what you give to the welder to tell them to make the weld. But the PQR contains all of that extra information that you know was good. So if you guys are actually interested in ever finding welding procedures, say you're looking in the pipeline world, see if I can throw this up here. If I just Google NEB, I'm going to use Enbridge because I know they have it, pipeline welding procedure. Because it's a matter of public record, you're going to find, hopefully, we'll add a little bit more information just to get through all the Google hits. SMAW. Right here, first hit is a welding procedure from Enbridge. And I think it's going to make me download it. We'll see if that'll pop up for you. It's over here. And that's what this looks like. So this is a welding procedure database, or data sheet, or your welding procedure specification as we're calling it. I mean, those two terms are kind of interchangeable, but this would be your WPS. So this you're seeing, it tells you exactly what it's being applied to, tells you what materials you can use it on, what the pipe size you can use it on is. In this case, because it's a high strength low alloy steel, they're going to specify a preheat temperature, and tell you what time you can have between interpasses. All of this information gets provided to the welder. It tells you for each pass what parameters you should be using, what your travel speed's allowed to be. Now this is a little bit interesting. In the world of pipeline welding, heat input is extremely critical. When you qualify welding procedure, you're allowed plus or minus, I believe in Z662, it's 10% from your heat input. That's not a very wide range. So typically when they're qualifying a weld procedure, people may or may not weld it under exactly the conditions they want. If you know that you want a heat input that is kind of as practical as possible to give yourself the widest range to work with, typically when you're qualifying procedures, you might tell your welder to try to put as much heat as they can in, and you're going to tell your other welder to put as little heat as they can in, and that's going to give you the widest range of procedures. Now, this is not always the best approach. You guys probably can understand, having gone through, for most of you, 3 or 4 years of engineering. If we're telling our welders in our qualification to weld parameters that are on the high end and the low end, we're not actually ever testing, hopefully, where we are 90% of the time, which is in the middle. So depending on what procedures you see, you may or may not see really wide ranges for travel speed and heat input, or you might see relatively narrow ranges, which are kind of realistic. But either way, if you're welding this, you can't go outside these ranges. Now for travel speed, I say it's interesting because does anyone know how you measure travel speed on a weld? Any guesses? You time it. So it's not really the travel speed that you're measuring at every instant in time. You're measuring the average travel speed over a long period of time. So typically, you're going to not have as much trouble maintaining a travel speed within these parameters, because if you're a little bit faster at one point, a little bit slower, it's not going to get picked up. Now from a understanding of heat input, that's a problem, because as engineers, we know that at each point in the weld, if our heat input spikes, it's going to affect the material there locally. The material doesn't care that our average is within the bounds. We could have very different microstructures if we're faster or slower in one spot. So although this procedure tells you hopefully what you need to do to make a good weld, there's always going to be a bit of engineering judgment, a bit of interpretation to make sure you're not just trying to do the absolute limits of what the procedure allow, but actually make a good weld. So this, you guys all saw how I got here. If you're interested, I encourage you to Google it. This is just one example of welding procedures in the structural world. There's a slightly different format in the world of welding for, say, automotives. There's a different format. But fortunately for pipelines, because you have to submit them to the government, they're all online. So, let's see for a second here. There we go. Maybe. Okay. So this procedure handbook is not really focused on pipeline welding because pipeline welding is kind of its own world. But for pretty much everything else that was, just not governed by a specific code, whether it was structural work, there's a specific code for steel construction. If it's pipelines, there's a specific code for pipelines. But everything else that's not in kind of those two big environments, if you want to weld something, this is the kind of reference that is going to get you kind of a relatively good starting point. So to talk about, first, let's consider a very specific example. So we're going to do a butt joint on 3/8 structural steel. So something like this. Now I'm not drawing a joint preparation here because that's something that would be in the welding procedure. But this is what you're seeing if you're in the shop. You got 2 pieces of 3/8. Of an inch, or 9.7 millimeters, give or take, steel, butt joint. This is all you've got. This is all an engineer has when they go in the shop. They got 2 pieces of material, they need to stick them together. How would you guys do this? Anyone? You weld it, of course. Okay. What might be some things you're thinking about? So if you're trying to come up with the best procedure for this, what are some things you're going to think about? Yeah?
What is the material that I'm welding?
Okay, excellent. I didn't put that here. We'll say this is A36 structural steel. So this has a minimum specified yield strength of about 250 megapascals. So relatively low carbon, nothing crazy for strength, no weird alloying elements. What else though? Now that we know this, what might be some things we're thinking of? Typically we're working for a company where there's going to be some money involved, so maybe cost. What else?
What service it's going to be?
Okay, application. Sorry?
Suitable electric procedure, like the method.
Right, so yeah, what different procedure we might be using to make it. So I'll say process. And a lot of these are going to be driven by other things. Like I drew this just kind of in the typical orientation, but what if this is an overhead weld? Some procedures are not going to work, some processes are not going to work for an overhead weld. What if this is part of a really big component that you can't really maneuver and get anywhere? So if you want to do it with an automated process, you can't position it under your gantry. That's all going to come into play. Typically,
Fix the position.
right, so there's things, there are industries such as the automotive industry where they'll take an entire car and maneuver it around to get in position for welding. But if you start to deal with, say, a huge structure for the oil field, that's not something you're going to put on a gantry and be able to move around. Typically, that's something where the welder or the welding machine is going to have to come to the structure. Something else that's not on here, what about time? How long it takes to make these welds? If you're making one, maybe it's not a big deal. If you're making 100 of them, if you're making, 200 feet of weld or 60 meters of weld, do you think time starts to come into play? It's not just the cost of actually the consumables that goes in. It's the cost of the welder. It's the cost of the time it takes you to position it, to grind out between passes. All of that comes into play. Anything else you guys think? Is this all that we care about?
The material.
Right, so we talked about the material here. So obviously if we're dealing with a structural steel like this, we're going to want to use a filler material that's appropriate. I don't think we've covered that in class yet when we talk about the welding design section. Depending on the code you use, we can tell pretty reasonably what would be an appropriate filler material for this. This 250 megapascals, oh, my conversion to KSI is not perfect. I think that's give or take 40, 39-ish KSI. So you'd want to make sure you're using a consumable that typically, if you're doing a butt weld, you want matching strength, but we're going to cover that all later. Now, consumables are graded based on their specified tensile strength, not yield strength. So maybe a 60 KSI, depending on what the tensile strength of this is, might be reasonable. Typically for structural applications, you don't have to worry about that. For each grade of steel, it's going to tell you exactly what the acceptable matching filler material is. So cost, application, process, material, time. Location, yeah. So you like location on the structure, field, shop, yeah. That's definitely a big one. I think we've learned there's a lot of processes that work really well in the shop, maybe not so well in the field, or if they're going to be applied in the field, you need much more equipment, there's much more cost. Something we didn't talk about here, but we talked a little bit about material, a little bit about process. What about heat input?
What about the temperature of workpiece in this case?
Right, so that would be kind of whether we need a preheat. Yeah. And that also comes into the environment, because if you're welding this out in the field in minus 30 degrees in Alberta, preheat doesn't necessarily mean bringing it up to 100 degrees Celsius. It might mean just bringing it above zero. But you want to make sure, typically for any application where there's toughness requirement, that whatever temperature you're welding at, you tested that weld at that temperature when you qualified your procedure. So preheat, environment. I mentioned heat input because I think most of you would agree that's a big one. There might be procedures that are of a fairly low cost. Maybe they're really quick. Maybe they're even using the right filler material suitable for the material. But the heat input is going to be high, and so we're going to need either a high preheat to try to change our cooling rate to make sure we get a good microstructure, or we're going to need to apply a post-weld heat treatment, all things that may or may not then change the cost, change the time. So heat input's typically a really big one. So we've got, I think, about 20 people in the class. So I'm going to suggest that everyone kind of from right down here to this side is Group A, and the rest of you are Group B. So Group A, your boss, he's a materials engineer. He's really concerned about heat input. He wants you guys to find the procedure that's going to have the lowest heat input possible. That's his goal. He knows maybe not a lot about welding, but he knows that heat input's a good thing. So he's told you to find an extremely low heat input material or procedure for this material. In addition, I want you guys to consider one other. Each one of you can kind of choose independently. Actually, well, I'll help you out. So you guys are probably going to be working together. There's two of you, and I see only one of you's got a handbook. So you guys have a part that's going to have not a great cut on the edge. Okay? So the edge preparation is not smooth. So you want a procedure that can tolerate that, low heat input. Yeah? Okay. You guys working together back there? Okay, same thing, low heat input, but you can't get to the back side. Something like a pipeline weld. Okay? So you can only weld from one side. Limited to procedures that can be only welded or ground from the first side. You guys are working together as well? Same thing, heat input, but something that's going to be in the field. We talked about here is a concern. And you don't have a book? Okay, so can you work with them? I think I divided you guys in half, but you're sitting side by side, so you're going to be on this side now. Because you don't have a book, right? Okay, so you guys are going to be on the heat input side too. Large, heavy assembly can't be moved around. It can only be welded in the flat position. That's the way the orientation of the part is. So no procedures that are going to be overhead, nothing that has to be vertical. Make sense? So you guys have a completely different boss than these guys. You have no idea who their boss is. Your boss is a business guy. He wants you to spend as little money as possible. He wants this weld to be as fast as possible. That's your goal, okay? So you want to make a weld that is as fast as possible, but like these guys, you got different requirements too. So it's not just as fast as possible. Big part, can't be moved. Same as them, except they're worried about heat input, you're worried about speed, okay? You okay being by yourself? As fast as possible, but field weld. Can't use anything that has to be done inside. There's two of you back there. Okay, same thing. As fast as possible, but you can't get to the back side. Something like a pipeline can only be welded from one side. And you guys, fast as possible, but rough edge. Not really good edge preparation, so a procedure that's going to be tolerant. Typically something that's a manual procedure where if the fit up's not perfect, someone can manipulate the torch and kind of adjust for that. Okay? And then you guys, there's two more groups. Do you want to, I know you guys have got a book, do you want to work with him though? Just so you guys aren't both by yourself? Yeah? Do you remember what your procedure is? Perfect. And you guys, the last group? Okay. So as fast as possible, and see what else. As low distortion. So you guys learned a little bit about what affects weld distortion. Typically, different high heat inputs going to have weld distortion, but I think we talked about different bevel preparations also have more or less distortion. Okay, so I'm going to give you guys about 10, 15 minutes to try to look through the book and find the procedures that fit those requirements. Yep. Oh, you don't have a book? Okay. So. Oh. I'm going to break my rule and I'm going to give you guys this one to borrow, but take good care of it.
I think you've seen that we walk past the construction site and they, like, you can hear them welding, but they have like these tarps set up so that they can use whatever process they want if the wind doesn't screw them. Where there's a well, there's a way. Let's tarp it off. Let's just take the lowest heat input and we'll specify tarp it off.
Lowest heat input process.
Unless they're telling us that
We can't afford tarps, we should afford to weld.
so we can. So it'll still have to be an arc process, not a beam process. Bigger tape. Bigger tape. Yeah, so we'll do take and we'll tarp it off. And then we get the best of both worlds. Get the process that our boss wants.
How are you guys doing?
We get the low heat that our boss wants.
Friction stir welding typically wouldn't be used for steel. I think we talked about it. The tools for steel are typically very fragile because they have to be made of something that can handle the high heat involved in steel. So especially something like a 3/8 inch steel, that'd be pretty thick to do with a friction stir weld. Even on aluminum, you think if you can only weld with 2 passes for friction stir, each of those passes would have to be about 3/16 thick. That's a fair amount of material to be welding through with a little tiny tip in a strong material. So you guys found the procedures, yeah, section 6?
Yeah, around.
Perfect.
Well, he doesn't really care about heat input as long as it's cheap, right?
Yeah. You guys are doing well. You found the procedures. Awesome. Section 6. Did you guys find the procedures?
Yes, we were thinking about the flux core
Okay.
reception.
Yeah. So in addition to the process, you guys have to provide some parameters, right? So you're trying to make sure that you've got a set of parameters you're going to give to your boss, and then you're going to qualify a welding procedure based on this. So that's a good place to start, but now you got to find some parameters in the book. So section 6 has everything on welding carbon steel. Can I get your attention for just a quick second? Everyone, just to make sure you guys know, ideally, we want to get some welding procedures by the time we're done here. So in addition to specifying a process, I want you guys to try to find an actual value for the current, the voltage, the wire feed speed, the parameters, all of that stuff you guys are going to be able to find in this book. So let's see what we come up with for procedures, but get the information you need to give a welder to go and make a test weld.
Is there a section?
Yeah. I do that.
So
Let's do this. Those are follows.
So you guys are focusing on time, right? So hopefully you notice there is something here that's going to tell you the total time required.
look at the time.
But make sure you consider for something like a shielded metal arc welding process, is that going to be the total time? This is how long it takes to physically make the weld. If you're doing something that's manually, you might not be able to spend 100% of your time. So take that into consideration. There might not be an exact quantitative value in here, but you can think reasonably, okay, how long would it take to get a new electrode? Compare that to a process that's on a wire that can just run continuously. How are you guys doing?
Okay,
Yeah.
It's not for summer job welding for one part. Does it have to have a back plate?
So it depends on what kind of procedure you're doing. Typically, there's either a backing plate that's made of copper that then you remove, or it's got a steel backing which may or may not be removed. But because you've got a really high current, really high voltage, if you're going to make it in a single pass, you can't just make it into space behind. You can't really do an open root pass with submerged arc. So there might be some procedures you find in here that are welded partway through and then welded from the second side afterwards as kind of a...
So if you can't access the other side, the inside, you can't use this process.
It's not ideal for where you only have one side access. So typically, because you guys, that's your requirement, right? So you can only access one side. Yeah, so for single-sided access, you're going to see, yeah, although submerged arc is a really efficient process, it's really fast, it's easy to automate, it's not great if you can't get access to the backside. There is one option which I don't know if is listed in here, but you can think, say you wanted to make this process. What would you do if you only have access to one side? You can't do an open root weld with submerged arc. You could do the root with something else. Now you don't have an open root. You've kind of got something similar to a backing, and then you could do a sub-arc on top of that. Won't be quite as fast because you have to make that first pass, but you can make most of your weld with submerged arc. For 3/8, it's borderline whether that would be more efficient, but for really thick plates, might be worth it. How are you guys doing?
Good. We picked an electrode. We're trying to figure out the diameter that we need.
Okay, and this is for which process? Shielded metal arc welding?
MIG.
MIG?
Yeah.
Okay, so you're in the shielded metal arc welding section. So these are going to not be for, these are for electrodes for stick welding.
Oh.
So,
6.2 was supposed to be like Oh no, this is the wrong section.
Well, let's hop back. It should be It'd be good.
right, and what you should see is when you go into the actual procedures, it's going to tell you for each kind of thickness in each procedure. Keep going, I think. Yeah. So it's going to tell you what recommended electrode diameter is, and for some you'll see, I think once you get to the thicker plate, it'll give you two different diameters, or even here. So you get two different diameters for the same thickness, but it's going to have different heat input, it's going to have different time. Typically you'll see that larger diameter electrodes are probably going to give you more material down faster, which for heat input might not be a good thing, but for speed is going to be great.
Right.
We were thinking Gmail pulse
Okay.
for edges and
Yeah. So did you guys find any procedures for pulse welding in there? I can't remember. This book might not have pulse in there. I'm not sure because it's a little bit. It's not. I mean, it's printed recently. I think 2005, but it might not have advanced waveforms. So pulse is probably one option. Now, you guys, what was your second requirement? Was single-sided access, or?
just low heat and bad edge.
Oh, bad edge, right. So definitely should work. It's a manual process typically, so that's going to give your operator some room to kind of adjust for the edge. Take a look through. I think you'll find that typically when you're welding a butt weld like that with MIG, you wouldn't necessarily use pulsed for the first pass. You'd use something like short circuit or STT, because you want a kind of a slower but really low heat input weld for the very first one. And then after that you might use either spray or something else to build it up. You also could weld with two sides and use pulse. So see if you can find a procedure that's going to say, okay, if we're welding 3/8, how many passes, which side are we making the passes from, and exactly what heat to put it. Yeah?
So what did you mean by one side Is it like, did you mean like one position only, or?
So if you're welding, think of like a pipe. So if you're welding a pipe, especially if it's a small diameter pipe, you can't get inside to weld from the inside. So everything you do has to be from the outside. So a procedure like submerged arc welding, where you might want a backing piece, that's not going to be very practical to put in there. Or a procedure that requires you to weld from then gouge the backside and weld from inside. For a small diameter pipe, you can't do it. Maybe a large diameter pipe that's kind of short, someone could crawl in and do that weld from the inside. But small diameter, you're limited to welding just from the outside. Yep. Yep, if you have any more questions, just let me know.
So we've got to a stage where we know we want hot wire, TIG, and that we can just
Okay.
use. We can set up tarping, because I wouldn't see so many tarps in the welding sounds if you couldn't do that.
Okay. Now, the one thing you might run into, I don't know if there's hot wire TIG procedures in this book. So you might have to specify some TIG procedures, which would be a manual TIG, and then just kind of try to estimate what kind of parameters you'd use for hot wire. But certainly you can, you're not limited to the procedures in this book. It's a little bit as kind of a jumping off point, because it starts to get you thinking about what you need to specify in a welding procedure. But, so you guys, do you have a question about?
We wanted to know, how can we find like the TIG procedures, because we're lost.
Okay, so you guys found them. I think they're in section 6.7.
Oh, wow, we're really behind.
I think,
6.7.
let's see. Let's see how my memory of this book is. It's not a very long section on TIG welding.
That's really far. press metal art processes.
Yeah. Yep, so welding carbon low alloy steels with TIG. So this will give you some procedures to use for TIG welding. For hot wire, typically you'd be able to get slightly higher deposition rate without increasing the heat input quite as much as if it was cold wire. So you can kind of use this as a reference point.
We want a small wire because we want the lowest heat input.
Right, yeah.
You said as low as
Yeah,
we can
absolutely.
We're taking this to the extreme.
That's good. What I want you guys to see is that when you start considering just a couple aspects, you get a very different answer than if you consider other aspects. Now, hopefully you guys realize in reality, you can never just say, okay, we only care about these two things, because although your boss in this case was a metallurgical engineer, his boss might care a little bit about the money. So, but in this case, no, that's fine. Now, do consider that if you're going to do a 1/16 electrode, think about, typically for hot wire, how small is that going to make your weld pool, and is that going to then limit the size of the hot wire you can feed in? But I think it's going to tell you what electrode diameter to use for certain material thicknesses, and I would stick kind of within the range it recommends. How are you guys doing?
we have best design.
We calculate the heat input for sub-art.
Okay.
Found some parameters. We're trying to find stuff for like TIG and make it. Well, TIG would obviously have lower heat input than just sub-art.
Right.
We may find a procedure where it has the correct thickness.
Okay. For TIG? So I think 6.7 is TIG welding.
And we have just looked at it, and we find that the maximum thickness for the TIG welding is much smaller compared with over 18.
Right, so then maybe TIG welding for this thickness of plate might not be your best choice. Now I do think there is a procedure for TIG welding. I think there is a procedure for 3/8.
Oh, okay.
However, I would agree with your assessment that for this thickness, in practice, TIG welding is not likely. Even though it's got low heat input, there's probably something that has also relatively low heat input, but also is not quite as operator intensive. Because I think, what was your other condition in addition to being
Like you said, it was just flat position.
flat position, right? So you could use TIG welding. But make sure you look at the other options too, because you know in practice, although TIG welding has low heat input, you're never going to just be limited to low heat input. For this, totally okay, but make sure you do look through the other options as well.
Okay.
Is this kind of going to make things difficult or what?
So steel backing is used for welds when you're open root. If you want to put a lot of heat input and you want to make sure you get a high quality weld on the backside. So depending on what you're doing, you might use steel backing, where it can be left in place or can be removed after welding. Now you can imagine removing it after welding is a very intensive process. If you're trying to do a weld as quick as possible, then specifying someone has to go remove that backing is not going to be great. Or you can use copper backing, which is reusable, or copper or ceramic, where you leave it in place while you're welding. Sorry?
Is there no possibility of bonding with the weld?
Typically for submerged arc welding, you wouldn't do a single pass weld without some sort of backing. Now there are some procedures in here, I think, which either use, in this, this is a 2-pass procedure welded from the side.
But it requires more than one pass. Like you have to weld from both sides.
Right, but depending on if you think about the time it takes to remove the backing or to set up the backing, might be faster still to weld from 2 sides. I can tell you for double jointing of pipelines, I think we talked about this, that's what they do. They have 2 submerged arc welding heads, and they weld it from both sides. Sorry, not for double jointing, for long seam welding. But there's other techniques as well, ERW. But it is a possibility.
Is this what we are like looking for? Like, is this what you ask us?
There's no wrong answer to this question, as long as you think about why this might be better than something else.
Again, how
we can know how to use this.
Right, and understanding that, okay, if you're looking at this and you're trying to minimize cost, there's other costs besides, or minimize time, there's other times beside this time. There's other costs besides, I think it tells you the pounds of electrode you use, the pounds of flux. There's also the cost of the equipment. All of those things are going to come into play.
So,
Yeah.
so we only need to make the weld faster, or we have to consider other factors.
Well, in your case, you're supposed to be considering, what was the other factor I gave you?
Faster.
Fast.
And what
Okay, well, I'll give you another one then, cost. So fast and try to, fast and cheap, okay? But you can think about what's gonna, I mean, usually there's some benefit. You're trying to do it fast. You're trying to spend as little time. There's gonna be less cost to the people operating. But equipment costs,
Right, so you think this is going to be
Looking at this one, for 3 gauge.
yeah,
You see current. This is positive.
yep.
Then voltage 33. Then is this on the? This is like low voltage, not on the high side.
Well, that's for two different passes. So pass 1 is 33 volts, pass 2 is 35 volts.
So it's normal voltage, or it's a low voltage, or high voltage?
Yeah. Can we classify this one like as low voltage word, high?
What do you mean?
In this range, like 33, 35. Is this on the high side or on the low side?
For submerged arc welding, because you have typically higher current, you're going to have higher voltage. Now you also have larger diameter wires, so it's not always like you see your diameter of your wire is going to reduce the resistance, which means you need more current to melt it, but it also means that current's going to produce less of a voltage drop in your wire, but you also might have a longer stick out because you're giving it, so compared to MIG welding, this is going to be a higher voltage. But if you remember when we were doing TIG welding with helium, we were up in the 30 volts. It's a totally different process. So it's not just about the voltage, it's also depends on what the process is, where that voltage is going. Yeah. Yep. How are you guys doing?
Sorry?
How are you guys doing?
Keep going.
Yeah? So you guys, you're trying to minimize time, right? As fast, and then the second, and cost? Yeah.
Also, I remember you said it's continuous, like not very flat.
Right, so a manual,
Maybe some.
right, maybe it's either, or it's, think it maybe it's a long piece where it's not cut perfectly straight, so as you're welding, your gap is going to get larger and smaller. So if you think of like the worst case would be trying to weld up with a laser. If you've got a gap that's changing and you got a very small diameter laser, it's not going to work. Now typically you wouldn't use a laser for a 10 millimeter piece because you need a huge power. But other processes like automated processes where you don't have the ability to kind of adjust for that change in gap wouldn't be as well suited. So I'm going to give you guys about 5 more minutes to keep looking, and then we're going to all come back together and talk about what we found. Yep.
Okay, so we found this, but we're confused.
Okay.
You gave us that it should be like a really low cost weld.
Yep.
So we have like two players here. Like one is flux core, the other is the stick welding.
Okay.
Flux core, as we learned in class, we just that says that it's better for pipeline welding in terms of giving you better weld, better efficiency.
Okay. Yeah.
And so we were thinking if this is, the number of pieces here are like say 5, and that's all that needs to be welded. We could use a stick welding procedure and find something that's
Okay.
because That way we're saving time.
right?
And also the cost comes down. Although there is an issue about efficiency because it depends on the weather then, completely the skill.
Right.
So other than that, I had a question. Like, how do you associate the 36 steel to this piece of information?
So typically most of these procedures would work on structural steel, low. So these procedures are given for low alloy and low carbon steel. So the exact wire you use, so I don't know if these give you a specific wire, do they?
They do.
They say E70-4. So these are assuming that your material is, you know, such that a 70 KSI electrode is going to do well. Typically that's not a bad assumption. Like low strength steels are kind of typical steels. Like this is the plates that we weld on when we do the hands-on in the lab. A 70 KSI electrode would be, I believe, at least matching, or it could be a little bit over-matching. It depends a little bit on what you're trying to do. So for a pipeline weld, you're always going to be making sure that your weld is exactly the same strength as your surrounding material. And typically for a butt weld, it's kind of the same. If you think you've got two plates and you join them together, you want to use a strength of electrode so that the weld's not the weak point. That's unique to this situation. Say you're using a fillet weld. You're never going to necessarily have the same area on your fillet as you will on your thickness of your, say it's the T-section of the flat plate. And if you make that weld bigger and bigger, it's going to be stronger and stronger. So there's not a limiting factor. You could use a lower strength material and make a bigger weld.
Because you have more deposition.
Well, because a fillet, you can make more weld. For a butt weld, you can't make a weld bigger than the thickness of your plate. Well, it's just, at some point, your thickness of your plate's your governing point, right? So, but for a fillet, you can make really big fillets. Or if it's say it's a stitch weld on a lap joint, same thing. You can make stitches. You're not trying to get the full strength of your material. You're trying to transfer whatever load is required to be transferred. But these procedures are kind of assuming that you've got a low strength structural steel. A lot of them you could kind of use as a jumping off point for different applications, as long as you realize if you're welding something that's a higher strength steel, you probably can't just use a regular 70 KSI electrode.
But for example, I want to make a PQR.
Okay.
I walk into there and they say, okay, let's make one, and that is satisfactory. I use this and I make one for 836 steel. That would be satisfactory for them?
Depends on what you mean by satisfactory. So if it's a code work, if it's for structural construction, you can open the code and it's going to say the strength of a weld must use this electrode, or a weld on these materials must use this electrode, or must be sufficient to design or to transfer the load as per the design. So if your design says, okay, this weld has to transfer 60 KSI of load over a weld that's 5 inches long and X amount thick, you can test that by figuring out how much you pull your weld in tension. You figure out when it breaks and say, yep, we're good. Not typical in the structural industry because people are just going to use the guidelines in the code. But say you're building kind of a weird assembly for part of a car. You might not do a small non-destructive test or a small section. You might build one of those assemblies and subject it to an actual physical test that you've decided internally, okay, it has to pass this test where we smash it into a wall at 100 kilometers an hour without sufficient failure. And then that is your testing to qualify that weld. Now your procedure still has to be qualified so every weld you make is the same. So you have to keep track of what you did when you made those welds so that you don't have to crash every assembly destructively because then you're not making anything.
So this book, if every industry has its own code.
Pipeline and structural are kind of the two industries that have their own code. Pretty much everything else you're welding is governed by a combination of requirements by the person who asked you to make it and internal company requirements and just design requirements. So there are applications where you wouldn't have to worry about this because the code is telling you exactly what your requirements are. But even if the code tells you you should be welding with 70 KSI electrodes on this material and you should have this much strength, you still don't necessarily know how many passes you should be using, what diameter electrode, there's still some room for interpretation, right?
That's why this concept.
And that's where something like this gives you a starting point, where if you're thinking, okay, if I want to weld with 0.45 electrode, what's the first setting I should turn on the machine? Should I turn the current to 300 or 150? Should I turn the voltage to 25, 40? It's a starting point.
What is the method to find all these parameters?
To find like the parameters for what you should. Well,
because you have so many methods, but we know the material, but there is no association between the material and the methods.
So what he's saying is that all of the low carbon that we are in,
Low carbon.
all of them are. So then this could be the generalized.
Right. So the one thing you'll see is if you're welding like a high alloy steel, you might find that the parameters here are not going to be suitable because you're not going to get the microstructure you want. Low carbon steels are a little bit less sensitive, so although there's lots of good reasons that you still want to maintain a fairly low heat input, they'll tolerate a little bit higher heat input. So these procedures are developed kind of as this is, like I said, this is not someone doing a fundamental understanding or theoretical analysis. This is people saying, okay, how have we figured out to weld this so they don't fall apart? Let's write it down so everyone else knows what we've been doing. But if you wanted to go from a theory and say, okay, we need to keep our heat input below this amount, we have this much material, we figured how much physical electrode we're melting, you can start to try to back calculate some of what they figured out, and you'll realize you don't get that far away. If you set one of your parameters like, okay, well, our heat input can be pretty high, but not crazy high, and it's a manual process, so the welder can only move so fast and keep control of the pool. And you can see once you start applying those kind of physical parameters, you'll get close. Now, you probably wouldn't get exactly to what these have, but you get close. But this is totally different side of the world. This is people just figuring it out by doing and then writing it down. But it's a good place to start. Does that answer your question? Yeah. You guys had a question?
So it doesn't have a 3/8 option, but 3/8 is like between 3/16 and a quarter, right?
Is it between 3/16 and a quarter? Yes.
But then
now,
keep flipping it, it just gives me another.
Now what it is between is it's between a quarter and a half, or it's between a quarter and 5/16, or no, sorry, it's between 5/16 and 3/4. And actually, I think there's 3/8 there, but that's not the same geometry we had. But you can, as long as you are interpolating between two procedures, yeah, you can use intermediate parameters, but make sure you're going between something that is on both sides of 3/8.
But this is only for
Right, so that's for a different joint. So that's not going to be what we'd looking for, because we want something that's for a butt joint. So. Yep, that would work. And you can, so between 5/16 and a half is 3/8. So choosing something in between there would be very reasonable. Okay. How's everyone doing? Does everyone have a procedure? Does anyone need more time? Relatively good? You need more time or you're good? Let's start talking about it, because hopefully you guys have figured out by now there's not really a wrong answer to this problem. As long as you thought about why you were choosing one thing and why that might not be better, then you did it correctly. If anyone did this without thinking, then I'm not even sure how you did it. So I really don't think there's any possible way to not come out of this learning what you're supposed to learn. So let's start with, I gave you guys your procedure last, so I'm going to let you guys go first. So, you guys, first off, do you remember what your requirements were?
Yes.
So
we need
fast,
low cost, and field weld.
low cost, and sorry.
Field weld.
Field, yeah. Right, sorry. Fast and low cost I kind of gave you. Those kind of go together typically, so we'll call that. And field.
Yeah.
So for now, just what was the procedure you came up with?
The procedure that we came up with was the flux core.
Okay.
And the reason, there were two, but then it also depends on other stuff as well. So right now we just stuck with this because it's higher efficiency than the stick welding. And also because we wanted it fast, we don't want any reruns. So we thought we'd go with the flux core.
Okay. Did you guys calculate a heat input for the flux core? No? Okay. While we go through, can you guys calculate a heat input and we'll put it up here? So I know heat input wasn't your main requirement. We're going to still see how it turned out. Next group, you guys? Not ready yet? Okay. Did everyone calculate heat input? Yes? Okay, I'm going to give you guys a couple more minutes. And can everyone calculate heat input for the procedure they chose? 2 more minutes to calculate heat input quickly.
Volts is 28.
I don't know 20% faster, but I think that
It's the same for all the solar arc.
so like for the current. Do that.
Remember one of the first few slides? He made us do it in class.
Okay, has everyone got a heat input now? Yeah? Heat input, most people? For those of you who don't have a heat input yet, keep calculating just as we go, but we can also do it as we go. So you guys have a procedure chosen? So first off, what was your requirement?
Submerged arc.
Okay, and what was, you guys were fast and low cost, but what was your other requirements?
Fast and low cost.
Okay, oh right, yeah. So you guys were just fast and low cost, just straight up. You guys were also trying to, no, you were on the heat input side? Okay, so we're gonna do all the people on the fast side first. What was your other requirement? It was kind of a rough edge, right?
Yeah, the two places are the firewall.
Yep.
And we choose the self-shielded front form.
Okay. And in the back?
We had so cheap, fast,
Yep.
and large part and low distortion.
Okay.
And we chose MIG.
Okay, and we had one more group that was doing fast, or was everyone else doing heat input? You guys were doing fast? Okay.
And cannot access the
Okay.
we chose flux core welding self-shielded.
2.0.
Okay, so the other side of the room, you guys were all trying to minimize heat input. So, one thing I do want to just clarify, hopefully you guys, most people here are materials engineers. So, A36 structural steel typically is not all that sensitive to heat input, not as sensitive as a higher carbon or low alloy steel. Doesn't mean we're not worried about heat input, but you will find that the procedures in this book, because they're based on experience and people working with structural steels, a lot of the procedures are kind of recommended to give a heat input that's reasonable for this material. If you were to take this book and try to apply it directly to, say, a low alloy steel or a higher carbon steel, you might find that even though the parameters in this book work well for a structural steel, when you go to higher grades of steel, the heat input recommended by these might be above what you can get. Doesn't mean it's not a good starting point, and you can start to understand how changing different parameters can affect your heat input. But just keep that in mind if you're ever using this. This book was built on people's experience, and most of that experience you'll see was with low-grade structural steels. That's why a lot of the electrodes that are recommended are kind of 70 KSI electrodes. No one's recommending in this book 120 KSI electrode to be used for welding, 1,500 megapascal automotive sheet steels. And that's just because of where this information came from. This wasn't theory. This was literally people looking and saying, okay, how have we been welding this? Let's keep track of what we've been doing and we'll tell everyone else so that they can do it too. And for years, that's how welding was done. Question?
Is arc speed the same as travel speed?
Arc speed, I believe in the terminology of this book, arc speed would be the same as travel speed. Which procedure did you find that for? MIG? Interesting.
Because we're trying to find the travel speed to calculate the heat input.
What page is that on?
It's in section 6.6, page 13.
Okay. Let's see, I think. Yeah, in this case, I think what they mean by arc speed is travel speed. The only time that arc speed, I think, might be different. In general, arc speed is not really a accepted term. Travel speed would be more appropriate, and that's typically what you'd see. The only time I could see people confusing the two is if you're doing a weaving process, maybe they would consider arc speed to be the physical movement of the arc, but that'd be more if you're programming a machine, and the maximum speed it can move would incorporate any side-to-side motion, but for a manual process, you're really just caring about your progression along the joint, which would be travel speed. So now we're on to the heat input. So we'll start with you guys. What process? Your second requirement was only flat position, okay. And what procedure? Sub-arc welding. Interesting. Sorry? With steel backing. Okay. So, and now hopefully everyone's had a chance to calculate the heat input now. So what did you guys get for heat input for this process? 30.6 kilojoules per centimeter. Okay, and the next group, what process did you guys have?
We chose TIG.
Okay, and your other requirement was field welding, right?
We decided that we're going to put in our specification that you have to chart the area before you weld.
Okay, so field welding with, or TIG welding with some sort of kind of tarps. And what was your heat input?
Our heat input ended up, because we're doing a hot water process, we have 14. Are you sure? 14.
141 kilojoules per meter. That doesn't sound right.
That sounds a little bit different than this one. So I'm going to have you guys.
14. I think it's 14.
Kilojoules, and then you said per meter or per centimeter?
Per meter.
That doesn't sound quite right either. I'm gonna leave that blank for just a second, and I'm gonna have you. Can you guys recalculate per centimeter?
It's 1,041, 17 kilojoules per centimeter. That seems really high.
So 31 kilojoules per centimeter sounds about right for typical process. I think we talked about it in terms of kilojoules per inch in one of the lectures, but this is not a crazy range. That sounds a little bit. You said 1.41? Because it's 141 per meter, right?
So 0.41, yeah.
Okay, well, we'll leave it there for now.
14.17, sorry.
Oh, 14 point? Okay, so 14, that sounds not bad. That's a little bit better. And then in the back?
Our requirement was for one side only.
Okay.
And we chose TIG.
Okay, and what was your heat input?
3.24 per
Sorry?
3.25.
3.25? That seems a little bit low as well. So actually, what was do you have the current and voltage and travel speed?
Voltage was 11.
Okay, 11 volts. Sounds about right.
100
Okay.
And it was 0.003387 meters per second.
Zero, it's about 4 millimeters per second, give or take. Yeah. Now, typically, so just so you guys all have a chance to take a look at this, I think this calculation is something you guys should all be familiar with now. My guess is at 4 millimeters per second, depending on what your joint fit up was, you're going to have to do probably multiple passes with this sort of parameter. So this is pretty close to what we were doing when we did TIG welding in the demo. So I think you guys saw it on aluminum, but you can imagine when we were doing it in the demo, we were putting down pretty small beads at about 100 amps, about 11 volts when we were using argon. I think 4 millimeters per second, how fast that's moving, that's a pretty good clip. To fill a 3/8 inch gap, depending on your bevel, you probably would need quite a few passes with this. So that's why our heat input's a little bit lower, is because you wouldn't be able to fill that up in one pass. So depending on, do you have the procedure you used in the book? What page is it on? Probably in section 6.7. Right, so if you look at, does everyone have, everyone look at page 6.7-7? So one thing you're going to see in this book is in those last two columns at the top, it's going to give you parameters for pass 1 and then passes 2 to 5. So it's a 6-pass weld. So this is going to be our heat input for about each pass, but our total heat input is going to be closer to about, give or take, 20, right? About 6 passes. So still competitive with submerged arc, but not quite so crazy different. Does that make sense to everyone? Awesome. And I think you guys are last but not least.
Low heat input.
Yep.
No smooth surface.
Okay, so rough edge. Run out of the room here, but. And what parameters did you come up with?
Yeah, maybe spirit transfer.
Okay. And what did your heat input end up being? 83 kilojoules per centimeter. That's lots of heat. So, what do you guys see? Do you think there's one solution for welding that fits every condition? No? Was it easy? Even with only 2 requirements, was it easy to find the perfect procedure? Right. So you can imagine if you're in a job where you actually have to do this for a living, it's not just one condition. It's all of these things that come into the selection. And that's where having kind of this knowledge that's been built up by people doing trial and error is helpful. It doesn't get you 100% there, but it helps you kind of understand all of the different considerations that go into this. And if you guys look through this book, there's sections on economics, there's sections on distortion, there's sections that describe each process. I really encourage you to take the time to look through and see some of the stuff that's in here, because it goes so far beyond everything we can cover in this course, but in a totally different side of things. So the theory from this course, combined with kind of the practical knowledge here, should be extraordinarily useful if you ever end up either in a job where you're designing welds, you're working with someone who's designing welds, or you're just working for a company in Alberta where pretty much every company in Alberta at some point is related to welding. We've had lots of students come through our lab as undergrads who then go and get a co-op job where they're working for someone. And one example that comes to mind, I had someone send me a message who was a DRA who worked with us and said, I'm working for a company that makes something with stick welding and they want to start using flux core. What should I do? I said, tell them it's a good idea. I don't know. That's not really what, did they ask you to do anything? And they wanted him to start to look at their stick welding procedure and see how they could make it into a flux core procedure. And obviously they'd want them to look at the trade-offs. I think for stick welding, I don't think anyone recommended stick welding here. Why might stick welding not be the solution you guys chose? Time consuming?
You have to put on a fair bit of heat for not a lot of deposition.
Yeah. What other reasons do you guys think stick welding might not be good? We didn't really talk about it here, but there's a big one that we talked about last class in the electrodes.
Start and stop, like you gotta.
Start and stop. What about hydrogen? Wasn't one of our requirements here. If you're trying to weld a material that you want to keep low hydrogen, sometimes stick welding, either if you have low hydrogen electrodes, you have to really make sure you're maintaining proper care of them, make sure you're handling them appropriately. Or if you're using 6010 or other electrodes that just inherently have high hydrogen, you're not going to be able to get those low hydrogen welds. And so there's a lot of reasons people might move away from stick welding, but it doesn't mean it's always the right answer for every situation. In typical pipeline practice, a lot of pipelines made in Alberta, I think we've talked about this before, are made with automated processes. But there's still a threshold. If you're making a pipeline that's 100 kilometers long, probably, and don't take my word for this, don't go work for a pipeline company and say, no, I learned in class 100 kilometers is the cutoff. It depends on the cost, but typically over 100 kilometers, it's probably going to be worth your while to invest in the equipment and do an automated process, or to at least hire companies that have invested in that equipment. But if you're making a fairly short pipeline, maybe 20 kilometers, maybe 25, you might find that it's easier to find people who know stick welding. You make sure you've got the procedures to handle the electrodes appropriately, and the cost of getting the equipment and the people to your remote area is going to be less because stick welding equipment's pretty simple, and it might still be the best solution. But it depends on what you're dealing with. There's not going to be one right answer. So we talked about a 3/8 inch plate. Did anyone find that the thickness was kind of a governing point? So who had a procedure they think would be different if it was a 1/8 inch plate? Yeah? What if it was a 1 1/8 inch plate? Yeah? You can imagine that if you're dealing with a really thick plate, there might be procedures you think about that weren't even in the book. Like we talked about electroslag welding. For pipelines that have thick walls, sometimes ERW is a common process. There's all sorts of considerations that even from this one situation, we saw it wasn't simple. What if it's a T-joint? What if it's a lap weld? What if it's aluminum? There's all these different things. And although this book doesn't cover all of them, it gives you a pretty good starting point for most of them. Did anyone find anything in the book that they thought was surprising? Has everyone who had this book kind of looked at it before, kind of knew what was in it? Yes, no? All of you? One thing I'll tell you is that in addition to this book, there's lots of other resources. So I got a couple other ones here. This one I think is really interesting. This one's called Design of Welded Structures. This book came out in kind of the 90s, and a lot of the stuff that was in this is now in the structural steel welding code. So we're going to talk about welding design, I think kind of in the middle of November. And when we talk about how you calculate the size of a fillet weld to transfer a certain load, we talk a little bit about why that might be important. A lot of the equations we're using are published in this book. A lot of the equations you might use to figure out how much distortion your weld's going to have, there's a little bit in here, there's a lot in this. And I think this book you might be able to find on Novel. It used to be on there, I'm not sure it still is, but same people who published this book, they make this one, they make another one that's on design of weldments. So welded structures would be more structural welding. This one's on weldment design. What I think is really interesting about these books is we've actually had, so the guy who helped develop these was a guy named Omar Blodgett, who worked for Lincoln Electric. And he worked there because, or he was doing this because for Lincoln they're selling welding consumables, and they were trying to make sure their clients who were buying their consumables were doing welding as efficiently and effectively as possible. So they would stay in business and keep buying welding consumables. And eventually he retired, and the guy who replaced him is a guy named now Dr. Dwayne Miller, who, as of September, is actually now an adjunct professor at the U of A. So he's come here already twice to teach courses that are basically one-day overviews of each of what's taught in these books. And he's taught 2 of them in the past, one in 2017 and one last year. And hopefully he's going to come again. Now that he's an adjunct professor, he's got a good reason to keep coming back to the U of A. So you guys might hear a little bit, probably next semester, about an opportunity to go to a course taught on design of welded structures, design of weldments. And I would really encourage you guys to take advantage of that. it's very unique that we have access to him to teach those courses. Typically, he teaches them in Cleveland, Ohio, where Lincoln Electric is headquartered. He's only taught them in Western Canada, I think, 4 times in the last 10 years, and 3 of them were at the U of A and U of C, or SAIT, organized because he is now an adjunct professor here. So just something interesting, I think, if you guys are ever interested in learning more about designing welds, it's a cool opportunity. The other thing I wanted to show you guys is, in addition to this, there's all sorts of little tools like this people have come up with over time. So this is kind of the really simple, quick and dirty version of this. This is what you do if you've got, say you want to do a flux core weld and you're standing in front of a machine. Someone thought, well, hang on, we should make it easy. So material thickness across the top, you do a slider to tell you where your material thickness is. Here it's 3/8. Then you can look and it's going to give you your wire diameter, your current range, your wire feed speed, your voltage for CO2 or CO2 argon. That's for flux core. It tells you another one for subarc. That's got to be the quickest way to come up with a set of parameters. Now, obviously this is not going to work for every situation. This is even more of just a kind of rough, experienced way of, or like a quick and easy way to get a starting point than this. But you can understand that for people who know nothing about welding, getting somewhere to start, someone who doesn't even have the knowledge from this course, if you're standing in front of a welding machine and you got to tell someone what parameters to use, there's so many different things to consider, so many different choices. It's a daunting challenge, and that's why I think it's awesome that this course is going to be taught, because hopefully now there's going to be at least 20 more people who know a starting point for welding procedures. There's also this one. So this one's mine. I think you can probably find these online somewhere. At one point in the lab we had a bunch of them, so I grabbed one. This is a little bit more confusing. This is actually a preheat calculator, and I have no idea how to use this. It's like a slide rule, but it's got a ring around the outside that helps you set your composition of materials. Then you get a hydrogen and you move it to set that. Then you flip it over and set your material thickness. And all of this is because people are trying to take the information that we're learning in theory, and rather than coming from the theory side, look at what they've been doing and try to then extrapolate it back so they can share that knowledge with other people. Hopefully, you guys are not going to have to start at this point where you're just relying entirely on the existing knowledge, because it's good to know what's there, but by the time we're done this class, we're going to know a lot more than just the experience of other people. We're going to have some fundamental knowledge to help get us started. So, aside from that, does anyone have any questions about the exam? Has any of this made you think of something you didn't have at the beginning of class? No? Okay. Then I think I'll see all of you hopefully on Thursday. We're going to have a hands-on demo of stick welding, so make sure you all wear same PPE we were last time. No synthetic materials. Make sure you're wearing closed-toed shoes, long pants. It's cold out, so that shouldn't be an issue.